Hey, welcome to another video. I haven't made a video in a while, so I thought I'd try to get back into the flow of things with a few A-level circles questions. These were sent to me a while ago and they're pretty spicy. I've got 4 questions here, I think. So let's see how we go with these. Alright, just a reminder, if you want to give these a go, remember to pause the video after I finish reading through the question and see if you can give it a go yourself. Okay, so this first question says a circle with center P and radius R touches externally both the circles x squared plus y squared equals 4 and x squared plus y squared takes 6x plus 8 equals 0. Prove that the x coordinate of P is a third R plus 2 and that P lies on the curve y squared equals 8 times x take 1 times x take 2. First, I want to draw a diagram. This is usually where I start when I'm given a geometric question like this and it doesn't have a diagram. I'll draw one myself. So we have 2 circles. So let's draw up our x-y axis first. All right. The first circle has a center at 0, 0. I can tell that straight from the equation. If you're not sure how I did that, watch my video on the equation of a circle and you'll see how you can tell the center is 0, 0 straight from the equation. It also has a radius of 2. So I can draw that in first. Okay, center at 0, 0, radius 2, something like that. For the other circle, I want to rearrange this equation a little bit to find the center and radius a bit easier. So this is going to be, well, firstly, let's write it out. Then use completing the square. This will be x take 3 all squared take 9 plus y squared plus 8 equals 0. So then we get x take 3 squared plus y squared equals 1. So that center is at 3, 0 and it has a radius of 1. So this would be 2. Center is about there somewhere. So that second circle would look something like this. Okay. All right. So let's just move that center over a little bit. Okay, there we go. Just a rough sketch is all that's needed. Okay, now we need to understand what this means if this circle with center P touches externally both circles. So touching externally would be something like this. So it just touches both circles from the outside, if you like. Touching internally would be something like this. So that circle touches both circles, but one of them is touching internally. So that circle would not be valid in this case. Okay, so we have another possibility. The circle could also be down here. But that's all. They're the only 2 possible cases, right? There's no other circle you could draw touching both externally like this. Okay, so we have 2 possibilities. In either case, the x coordinate will be the same. It's just the y coordinate that's reflected in the x-axis. Okay, firstly we want to prove that the x coordinate of P is a third R plus 2. Okay, where to start here? Where I began was looking at right angle triangles. Right angle triangles are often a really good place to start with these geometric questions. So firstly I began by drawing a triangle from the origin to the center P and then to the center of the second circle, and then I drew a line straight down to the x-axis. Okay, and I'll explain the reason I did this in a minute, but first I want to draw this triangle diagram separately and then I'll sort of walk through the different parts of it. So we have basically a triangle, a diagram like this. I want that to be a flat line. So this is a right angle triangle. So this length would be the y coordinate of that point P. So I'm just going to call that B. So if we label this point P A, B, this length would be B, this length would be A, and then we have this length split into 2 parts. This part is 2 because we're told the radius of that first circle is 2. This would be the radius of the unknown circle. So this length, the hypotenuse of this right triangle would be split into 2r. This entire length to the center of the second circle is 3. Okay, because we know that center is at 3, 0. And then this length is split into 1, the radius of the smaller circle, and r, the radius of the unknown circle. So this length is 1r. And also we have a little length here I'm going to label c. So the reason I did this was because I saw that I could relate the x and y coordinates to r pretty easily using Pythagoras. I'm not saying this is the best solution or the quickest solution. This is just the solution I used, and it seems to work. So this is how I would do it. Okay, so firstly, we can create 3 equations here. First equation is relating a, b, and 2 plus r using this right triangle. So I should have drawn it like that. So due to Pythagoras, we would have a squared plus b squared equals 2 plus r squared. We can create a second equation using this right triangle on the right here. So that would be b squared plus c squared equals r plus 1 all squared. And then we can create a third equation using just this length here. So a plus c equals 3. So now we have 3 equations with technically 4 unknowns, but we only need x in terms of r. So we can think of this as just having 3 unknowns, 3 equations you can then solve for x. And remember, a is effectively the x we're looking for, the x coordinate. So at the end, we're going to be basically saying a equals x. Just to remember that for the end. Okay, so we want a in terms of r. That's the point. We want a in terms of r. How can we do that? Well, firstly, we can get c in terms of a. So c equals 3, take a. Then we can write b in terms of a and r. And then we can finally write a only in terms of r, and we'll get our final solution. Okay, so let's start that down here. So plugging in 3 take a for c, we would have, we're taking equation 3 and putting that into equation 2. We get b squared plus 3 take a all squared equals r plus 1 all squared. And so b squared equals r plus 1 all squared take 3 take a all squared. Okay, then we're going to take that value for b squared, plug it into the first equation. So we're taking equation 2, plugging it into equation 1. So then we get a squared plus r plus 1 all squared take 3 take a all squared equals 2 plus r all squared. Okay, now we just need to rearrange in terms of a. So expand the brackets, or actually let's rearrange first quickly. So this would be a take 3 take a all squared equals 2 plus r all squared take r plus 1 all squared. And I'm sure you can manage this algebra yourself, so I'll just run through it really quickly. This would be 9 take 6a plus a squared. Then 4 plus 4r plus r squared, take r squared plus 2r plus 1. And keep going, keep simplifying. Those a squareds would cancel. The r squareds would cancel. We end up with 6a take 9 equal to 4r take 2r, 2r plus 3, right? Hopefully I haven't made a mistake there. And then add the 9 to the right hand side, so this is 6a equal to 2r plus 12. Divide by 6, we get a equal to a third r plus 2. And that is what we needed, right? X equals a third r plus 2. Remember, a was effectively x. So therefore, x equals a third r plus 2. Okay, that was the first part of that question. The second part was to prove that P lies in the curve y squared equals 8 times x take 1 times x take 2. Okay, a couple of things to note before we proceed. We now have the x coordinate of the center being a third r plus 2, and then something. We've labeled it b. We can rearrange r in terms of x, because x equals a third r plus 2, so we can say, let's write that out. Then we can say a third r equals x take 2, so r equals 3x take 6. So we can get r in terms of x, and what I'm going to do then is to do the kind of the reverse of what we just did. Substitute 3x take 6 in for r in this equation, and then get b in terms of x. Right? Hopefully that makes sense. So remember, a was x. So this equation is going to become x squared plus b squared equals 2 plus 3x take 6 for r. Okay, hopefully that makes sense. Just to rewind a little bit, what does this mean when it says P lies on that curve? So basically we're saying that I kind of misspoke at the start of this video, I'm realizing, because this circle doesn't have to be this size. It can be any size. What I meant when I said the x and y coordinates will be the same is that in relation to these two possibilities, they would be the same. But this circle could be larger, right? Could be like that, and then the center would be out here somewhere. The center would be out here somewhere. So we're getting a range of possibilities for the center, and we're going to find that those points lie on a particular curve. And they're related, so the x and y coordinates are related to each other by this equation. And the way that I'm showing that is firstly finding how x and y are related to r, and then how r is related to x. So we know r is 3 times the center take 6, and then we can just relate x and y to themselves without needing r. So that's the basic thought process that I'm going through here. So taking this equation, b is our y coordinate for the center. So now we just need to rearrange this in terms of y squared. So we've got x squared plus y squared equal to 2 take 6 is negative 4. So in the brackets here, we just have 3x take 4 all squared. Then x squared plus y squared equals 9x take 24x plus 16. That's 9x squared, sorry. Then we have y squared equal to 8x squared take 24x plus 16. Then factorize out the 8. I'm running out of room here. Y squared equals 8 times x squared take 3x plus 2, which we can factorize, that quadratic factorizes into x take 2, x take 1 as required. Okay, so that was the equation we needed. All right, hopefully that makes sense. You know, what that means when it says prove that the x coordinate of P is a third r plus 2 and that P lies on the curve y squared equals, etc. Okay, on to the next one. This question says, it's pretty spicy, this one. The circle S1 with center C1, A1, B1 and radius R1 touches externally the circle S2 with center C2, A2, B2 and the radius R2. The tangent at that common point passes through the origin. Show that A1 squared take A2 squared plus B1 squared take B2 squared equals R1 squared take R2 squared. Okay, this is the first part. Again, I want to draw a diagram just to sort of understand what's going on. So we have two circles with centers A1, B1, A2, B2. They could be anywhere. I'm just going to draw them in the first quadrant, but you know, I could draw them over here, over here. It doesn't really matter as long as we get a picture of sort of what's going on. Okay, so that's our first circle. Now the tangent to both circles, the tangent to both goes through the origin. So this tangent is going through the origin, and the second circle touches this first circle where the tangent touches both circles. So we have sort of this picture. The circles are just touching, and we have that tangent to both circles going through the origin. Okay, so we have the centers C1, C2, and we want to show that we can end up with this equation. Okay, so the first thing I noticed was that if we draw lines from the origin to the centers of the circles, and then we draw a line connecting the centers, we can create two right angle triangles. Again, with the right angle triangles. They're pretty useful things, right? So this line, these are two radii of the circles, so they must meet the tangent from the origin at 90 degrees. They're two right angle triangles, and these hypotenuse, OC1 and OC2, we can find in terms of A and B. So looking at this first right angle triangle, this one here, I want to look specifically at its hypotenuse, so OC1. Okay, so we're looking at the first part of this question. And I'm looking at the magnitude of OC1. What is the length of OC1 in relation to A1 and B1? Well, if we draw a line down to the x-axis from C1, we create a right angle triangle with its hypotenuse OC1. And the legs of this right angle triangle are B1 and A1, right? This length to the center is the x-coordinate of the center, in other words A1, and the other leg is the y-coordinate of the center, in other words B1. So this magnitude of OC1 is going to be the square root of A1 squared plus B1 squared. Okay, hopefully that makes sense how I got that expression. And then for OC2 we can do the same thing. That magnitude is going to be the square root of A2 squared plus B2 squared. Okay, so looking at this right angle triangle, I'm going to call this length in here from O, let's call this point X. O to X, I'm going to label that X, that length. This length from C1 to where the circles touch, that's the radius, R1. Actually, I'll get rid of that X, it's in the way a little bit. Then the length from C2 to where the circles touch is R2. Okay, so looking at this right triangle I highlighted in yellow, we can say, using Pythagoras, x squared plus R1 squared equals the hypotenuse squared, OC1 squared. So that would be the square of this, which is just A1 squared plus B1 squared. Okay, then do the same thing for this right triangle in here. Again, we have x squared plus R2 squared equals A2 squared plus B2 squared. And then we can relate these two equations because we know that x squared equals A1 squared plus B1 squared take R1 squared, and it also equals A2 squared plus B2 squared take R2 squared. So these two things are equal, therefore we can say A1 squared take A2 squared plus B1 squared take B2 squared equals R1 squared take R2 squared. So that's the first part, just basically finding OC1 and OC2 in terms of A1 and B1 and then relating them using that line from the center to the points where the circles touch. Okay, the second part of this question says, if also the other two tangents from the origin to S1, S2 are perpendicular, prove that the magnitude of A2, B1 take A1, B2 equals A1, A2 plus B1, B2. Okay, so we have two other tangents to the circles. They must be these two. That's the only other possible tangents. They are perpendicular, so they are at 90 degrees. So that angle in there is 90 degrees. Okay, now there's not much of a clue in this question as to where to begin, but I will give you a hint. There is kind of a formula you need here that we don't really talk about much in the current A-level curriculum, and it's this one here. So it says tan theta equals the magnitude of M1 take M2 over 1 plus M1 M2, and that's it. Now that is basically the sum formula for the tangent function, which you might be familiar with from trigonometric identities, but this is in a slightly different form that we don't really use anymore. But this formula makes this question much simpler. So firstly, we're going to note that, let me get a different color, that these two angles in here are equal because these are tangents to a point, and that's line OC2 bisects that angle. So if we called that angle alpha, this angle would also be alpha. And then also we can do the same thing on the other side. So if we called this angle beta, this angle in here would also be beta. And then we can see that alpha plus beta equals 45 degrees simply by saying 2 alpha plus 2 beta equals 90. So dividing by 2, alpha plus beta equals 45. Also, we're going to remember that the tan of 45 degrees is 1. That's kind of going back to absolute values in GCSE mathematics. And these are kind of the facts you need to answer this question. So this formula and these two things. Okay, so let's begin down below. So for part 2, we are firstly going to note the gradients, or the gradient of OC1 and OC2. So the gradient of OC1 is the rise over the run. So the rise is just the y coordinate of the center, and the run is the x coordinate of the center. So that would be B1 over A1. And then the gradient of OC2 is the same thing. Gradient of OC2 is B2 over A2. Okay, then we can say that the tan of alpha plus beta is the gradient of the first line, OC1, take the gradient of the second line. I should explain this a little bit more. So this is effectively as I said, the sum formula for the tangent function, and it relies on the fact that if you have a line, the gradient of that line will just be tan theta. So tan theta effectively gives you the gradient of that line. So that's where that formula comes from, by the way. So anyways, we have M1, that was B1 over A1. Take M2, B2 over A2, all over, I should move that down onto the next page actually, all over 1 plus M1, M2. So B1 over A1 times B2 over A2. Okay, and this equals 1 because alpha plus beta is 45. Okay, then we just rearrange. So because all of this equals 1, we can multiply the right-hand side by the denominator. So we get B1 over A1 take B2 over A2 equals 1 plus b1 b2 over a1 a2. And I'm sure you can manage the algebra from here, so I'll run through it fairly quickly. Combining the fractions, we get b1 a2 take b2 a1 over a1 a2, and then a1 a2 plus b1 b2 over a1 a2. This is always the absolute value. Then because we have the same denominators, we can get rid of those. So we have b1 a2 take b2 a1 equals a1 a2 plus b1 b2 as required. So that was the expression we were looking for here. I think I've just written them in a slightly different order. So b1 a2 take a1 b2 equals this. Okay, so that was the second part. The third part shows, hence show that if C1 remains fixed but S1 and S2 vary, then C2 lies on the curve. A1 squared take B1 squared times X squared take Y squared equals 4A1 B1 XY equals 0. Okay, what does this mean when it says if C1 remains fixed but S1 and S2 vary? All this really means is that we're leaving A1 and B1 as, you know, that center is fixed, but A2 becomes X, that's now a variable. This center here is now moving around, you know, depending on how the radius or the radii differ, how they change, and how, well, that's actually all that's changing, isn't it? Oh, these two tangents stay perpendicular, but the radii are all that are changing. However they change, this center here is going to move around, and that gives us variables for A2 and B2. So that's all that's really saying. A2 is now X, B2 is now Y. So we already have an equation relating A1 and B1 with A2 and B2. So we just need to work with this equation here. Now, if you have two values that are equal, the absolute values are equal, you can square them and then they are equal. So for part 3, the first step is to say that B1A2 take B2A1 squared equals A1A2 plus B1B2 squared. Okay, and then we need to do a whole heap of algebra here to try to end up with the final equation. So firstly, let's expand these brackets. So this would be, I'll write that around the other way. A2 B1 squared take 2 A1 A2 B1 B2. That's the terms you would get in the middle if you expanded those brackets. Then plus A1 B2 squared equals A1 A2 squared plus 2 A1 A2 B1 B2 plus B1 B2 all squared. Next, if we add all of those terms to the right hand side, we're going to have A1 A2 all squared take A1 B2 squared take A2 B1 all squared plus B1 B2 all squared, and then we have this 2A1 A2 B1 B2 plus the same thing. So that negative, we add it to the right hand side, so we end up with plus 4A1 A2 B1 B2, and all of this equals 0. So now we have these 4 squared terms, and we need to try to factorize this. So try to think of this as like a quadratic. How could we do this? Well, if the first term is A1 squared in the first set of brackets, and then in the second set of brackets it's A2 squared, that would give us A1 A2 all squared, right? If we multiply those together. Then for this second term, if the term in the second brackets is B2 all squared, that would give us, if it was negative B2 squared, that would give us negative A1 B2 all squared. So that term there. Then if this second term in the first set of brackets was negative b1 squared, that would give us this third term, and the final term is b1 b2 all squared. Multiplying those last terms, that would give us that term there. And then we have 4a1 a2 b1 b2 equals 0. And as we said at the start, because we're saying that c1 is fixed and c2 is a variable, we just need to replace the a2 and b2 with x and y. So therefore, we get a1 squared take b1 squared multiplied by x squared take y squared plus 4a1 b1 xy equals 0 as required. Okay, on to the third question. What do you think of those questions so far? Pretty good, right? Okay, this one says, show that the points negative 1, 0 and 1, 0 on the same side of the line y equals x take 3. Find the equations of the two circles, each passing through the points negative 1, 0 and 1, 0 and touching the line y equals x take 3. All right, diagram time. Let's draw it more like this. So I'll confess, I'm not exactly sure what they mean, show that the points negative 1, 0 and 1, 0 on the same side of the line. But I'm just going to draw a diagram here. So y equals x take 3 intersects the y-axis at negative 3 and has a gradient of 1. So something like that. And I guess what you could do to show that is show that they both lie to the left of the x-intercept and both lie above the y-intercept. But I'm just going to show you on the diagram. It's pretty clear they're on the same side. Okay, so here we have negative 1 and positive 1, 0. And we want to find the equations of the two circles, each passing through those points and touching the line. Okay, so we would firstly have a smaller circle here. Now this is kind of tricky to get right. So something like that. I'm just going to squish it up a bit. So that's a smaller circle passing through the points and touching the line. And then we have a larger circle. So it would be something like this. Okay, that's really bad. Yeah, this is kind of hard. Actually, I'm too embarrassed by this circle. I'm going to spend a few minutes trying to get this right and then I'll come back. Okay, that's a better looking diagram. All right, so we have our two circles. And as I was saying, the first thing we can note is that we have this chord here from negative 1, 0 to 1, 0. And the y-axis bisects that chord and is perpendicular to that chord. So the y-axis must go through the center of both circles. So we know already that the center of both circles lies on the y-axis. So let's make a note of that. Okay, so we know the centers are on the y-axis. In other words, the x-coordinate of both centers is 0. And so we already know the equations of the circles will be x squared plus y take something squared equals r squared. Okay, so that's the form those equations will take. The next step I took was to look at the perpendicular line from the tangent to this point, negative 1, 0. To begin with, I was just looking for, again, I was looking for right angle triangles to work with. So I began by drawing one, a perpendicular from the tangent to this point, negative 1, 0. So I just said, okay, that's 90 degrees. I want to know something about that line. Well, firstly, we can find the gradient. The gradient will just be the negative reciprocal of the gradient of this line. So let's say the gradient of y equals x take 3 is 1. Therefore, the gradient of that line is going to be negative 1. And then we can find the point where it intersects the tangent and the point where it intersects the y-axis. And then you will notice something interesting. So firstly, where it intersects the y-axis, well, it has a gradient of negative 1. So we go down 1 across 1. So it's going to intersect the y-axis at 0, negative 1, right? And then we go down 1 and cross 1 again to find this point of intersection. That's going to be at 1, -2. And then we notice, hey, wait a minute. The lengths on either side of the y-axis to the tangent are the same. What does that mean? Well, this line, the y-axis, was also the circumference of that smaller circle, right? So if that line we've drawn from -1, 0 to 1, -2 is bisected by that circumference, that also means it must be a circumference of that smaller circle. Now here I'm going to confess I'm not sure if this is a circle theorem, but I'm sure that it's correct. At least I wasn't able to find a counterexample. I think it's related to the fact that the radius is always 90 degrees to the tangent, and it's the shortest distance from the center to the tangent. That's how you prove that theorem. I think you could prove this in a similar way. I should probably look for a more rigorous proof here, but I kind of went with that. I just thought, okay, that's enough for me. This line is a circumference, and I will get back to this at some point and say, okay, here is the proof as to why this is the case. But in any case, I'm going to proceed with the fact that this line is actually the circumference of this smaller circle. And if anyone wants to help me out finding a more rigorous proof to that, and by the way, I need to redraw this because that line we now know is going through the center of the circle and is 90 degrees to the tangent. That doesn't look like 90 degrees. Let's redraw that center. And it's going through the center and it's 90 degrees to the tangent. So now in fact we know the center of the smaller circle is 0, -1, and we can also find the radius. It's just the hypotenuse of a 1, 1 right triangle. So we've solved the first circle, the smaller circle. So the smaller circle has a center at 0, -1, and it has a radius of √2. Okay, that's the distance from 0, -1 to 1, -2. Now we need to solve the larger circle. To do that, again, I'm going to draw right triangles. So I'm going to draw a radius from the center to the tangent, and I'm going to note that we have two similar right triangles here. This one in here, and this larger one. Okay, so they are similar because all of the angles are the same. And we can note this radius is going to be some multiple of the radius of the smaller circle. And this length here from 0, I meant to write 0, from 0, -3 to this point, 0b, that length is going to be some multiple of 2. That was that length there. So this is some multiple of 2, let's say 2k. Okay, so now that y coordinate of that center is going to be 2k take 3, right? From -3 to 0, that's a length of 3. That entire length is 2k, so we take that 3 off to find the y coordinate of the center. So for the larger circle, we have the center of 2k take 3, and we have the radius, some multiple of the radius of the smaller circle, so k √2. And now we're going to use this equation. Remember we noted that the equations of the circles was x squared plus y take b all squared equals r squared. Well, using the point we know lies on the circle, we can say then that it would be, let's say using 1, 0, we could say it would be 1 squared plus 0 take b, so negative b squared equals r squared. And then we can relate b and r directly. So we can say b squared equals r squared take 1. Using that equation, we can relate the center, 2k take 3, and r k root 2 to solve for k. And then we can solve the larger circle. So plugging these in, sorry, I shouldn't have said center. I should have said b. B equals 2k take 3. So now we have 2k take 3 all squared equals k root 2 all squared take 1. And then we have an equation we need to solve for k to find the larger circle, the equation of the larger circle. So this is going to be 4k squared take 12k plus 9 equals 2k squared take 1. Then we get 2k squared take 12k plus 10 equals 0. Then k squared take 6k plus 5 equals 0. Then we can factorize this into k take 5, k take 1 equals 0. And k equals 1 is the first circle. So that was where the radius was equal to root 2. So we don't need to worry about that solution. We care about the k equals 5. So now we have k equal to 5, therefore the center is at 0, 7, and the radius is 5 root 2. So b equals 7, the radius is 5 root 2. And so now we have the equations of the circles. Equations of circles. The first one was x squared plus y plus 1 all squared equals 2. And the second one was x squared plus y take 7 all squared equals 5 root 2 squared is 50. Okay, so that's the final solution to that question. Pretty good question so far. The last one is the final question in this video. This question says, find the equation of the circle S that passes through 0, 4, and 8, 0 and has its center on the x-axis. If the point C lies in the circumference of S, find the greatest possible area of the triangle ABC. Okay, first thing we do, draw a diagram. So let's draw up our axes. And we have a circle passing through 0, 4, and 8, 0. So 0, 4, let's say is here. 8, 0 would be something like here. And its center lies on the x-axis, so it would be something like this. Okay, that looks pretty good. And the center is here somewhere. And we have a point C such that the triangle ABC has the greatest possible area. So this was A, this was B. Okay, how do you create a triangle with the greatest area? What has the greatest height? Okay, so where would be the greatest height? So if I drew this triangle over here, let's think of AB as the base. Would that be the greatest area? Or can I create a triangle with a greater height? What if I drew this triangle? Yes, we can clearly see that height is larger or longer. So basically, to maximize the height of this triangle, we want the point that is opposite the middle of this line. In other words, if we draw a perpendicular line bisecting AB, the point C would be where that line intersects the circle. Hopefully that makes sense. So we're going to firstly find the midpoint of AB. So midpoint of AB, that would be 8 divided by 2 is 4, 4 divided by 2 is 2. So we have that midpoint, 4, 2. And we're going to draw the perpendicular, which must go through the center due to the bisecting chord theorem, right? A line that bisects a chord and is perpendicular to it must go through the center of the circle. Then where that line intersects the circle, that will be point C, giving us the greatest area, because that line has the greatest length, the greatest possible length we could draw. Okay, then we want to find where that line intersects the circle. To do that, we're going to need the equation of the circle. How do we find the equation of the circle? We need, well, we have this point, 4, 2. Let's call this point M. We want the center. So to find the center, we can find the gradient of that line, CM. So let's firstly find the gradient of AB. That's rise over run, so negative 1 over 2. And then the gradient of CM, that's the negative reciprocal of that, that would be positive 2. Then the center, if we go from 4, 2, we go down 2 and across 1, we'll get to the center. So down 2 from 2, that would be at 0, and then across 1 from 4, that would be at 3, 0. So we have the center equals 3, 0. And then we know the radius will be 5 because B was at 8, 0. So the distance from 3 to 8 is 5. So R equals 5. Then we have the equation of the circle. Oops. Plus y squared equals 25. Okay, so that's the equation of the circle. Then we want the equation of the line CM. Equation of CM. This is going to be y equals 2x plus something. If we use the point 3, 0, we get 0 equals 6 plus c, so c equals negative 6. So the equation of CM is y equals 2x take 6. Then we can find where that intersects the circle by plugging in y into the equation of the circle. So where CM intersects circle, we get x take 3 all squared plus 2x take 6 all squared equals 25. Now we need to solve this for x. So we get x squared take 6x plus 9 plus 4x squared take 24x plus 36 equals 25. Then we've got 5x squared take 30x. 36 plus 9 is 45. Take 25 is 20. Then dividing by 5, we get x squared take 6x plus 4 equals 0. And this quadratic is not something we can factorize. We can use completing the square instead. So this would be x take 3 all squared take 9 plus 4 equals 0. Then we get x take 3 all squared equal to 5. Negative 9 plus 4 is negative 5. Add it to the other side. Then we get x equals 3 plus or minus root 5. Okay, which one of these coordinates is the one we want? So we have this line CM. It intersects the circle at 2 points. This point would be 3 plus root 5, right? That's the larger point. So this one is going to be 3 take root 5. That's the one we care about. Now we need the y coordinate. So we can use the equation of the line, plug x in. So we want x equal to 3 take root 5, the smaller value for x. So then y is equal to 2 times 3 take root 5 take 6, which is equal to 6 take 2 root 5 take 6. In other words, y just equals negative 2 root 5. Okay, so we have that point C, 3 take root 5, negative 2 root 5. Now we want this distance from C to M. We can find that using the distance formula. Once we have that distance, we can find the area of the triangle, which is what we need to answer the question. So that that distance cm, the magnitude of that line is going to be the square root of the difference between the x coordinates and the difference between the y coordinates. Remember, m was 4, 2. And c is 3 take root 5, negative 2 root 5. So this is going to be 4 take 3 take root 5 all squared, plus 2 take negative 2, 2 take negative 2 root 5 all squared. So let's simplify. This would be 4 take 3 is 1, so this would just be 1 take root 5 all squared, and this would be 2 plus 2 root 5 all squared. Okay, what's the best way to simplify this? Well, if we factorize the 2 out from the second set of brackets, we would get, actually, by the way, this should be a plus, shouldn't it? So that was take negative root 5, so that should be 1 plus root 5. Okay, so as I was saying, if we factorize the 2 out from the second set of brackets, we would get plus 4 multiplied by 1 plus root 5 all squared, right? So factorize the 2 out and square it, we get the 4. Then we've got 5 lots of 1 plus root 5 all squared underneath the square root. And then we could write that as root 5 multiplied by 1 plus root 5. So the square root of the square, they cancel out, and we just get this. I think that's about as simple as we can get there. And then we need the magnitude of AB. That would just be the square root of 8 squared plus 4 squared. If you go back to the diagram, just looking for the length AB, that right triangle has legs of 4 and 8. So the length of AB is going to be 8 squared plus 4 squared. The square root of that, that is 64 plus 16, that's 80. So can we write that in terms of root 5? 5 times what is 80? 5 times 16 is 80, so that's 4 root 5. And then the area of ABC, think of this as the height. This is the base. So we just want to do base times height divided by 2. So let's write area of triangle ABC equals 4 root 5 multiplied by root 5 times 1 plus root 5 over 2. That's the area of a triangle formula. Then we have 4 divided by 2 is 2. Root 5 times root 5 is 5. And so we get 10 times 1 plus root 5 as our final answer. Okay, so that's the area. How did they say it? That was the greatest possible area of triangle ABC was 10 multiplied by 1 plus root 5. So there you go. They were some fairly spicy A-level circles questions. I hope you liked those ones. If you found this video useful, please leave a like. Let me know what you thought in the comments, and I'll see you in the next one. Bye for now.